So unit 3B, polynomials. Right, so this actually isn't that new for you guys. Well, maybe you don't remember it. I can imagine that. But this was grade 10, right? So we got linear functions, right? So this column right here is going to be what you guys did in grade 10. So that was graphs that looked like a line, right? And that was, I've got it written a little bit different here. This one's y is equal to ax plus b. But you might remember that more as y is equal to mx plus b, right? So that was a line. And then last year we did quadratic functions, right? And that was this. So that would have been these parabola shapes. We had a whole unit on those parabolas and how they behaved. So now, like, the new part of this, we're just throwing in like the next one up. So these are all types of polynomials. But now what we're going to be dealing with is a cubic function, which just means that the first term here, right, like the biggest term or like the biggest power, is going to be a power of 3, like something to the power of 3. And polynomials could go up too, right? You could have something like with a power of 4 or 5 or anything else, but that's as much as we go into in 30-2. So those graphs are going to look something like this. They're going to be like a weird little squiggly. All right. This table that I've made you guys here is actually going to be pretty important for what we need to do for polynomials. So I'm just going to go through it really quick and then go through some other stuff here. So here's some examples of your linear functions, right? So linear functions, here's some example of quadratic functions. Notice, just kind of remember that you can write these things as y is equal to x minus 4, like something like that. Or it can be written like this: f of x is equal to yada yada, right? So it can be either one. And the next part here, well, let's go back into like what a polynomial is too, right? So a polynomial function that contains only the operations of, so it will only be multiplication and addition. So what that means is like this, right? So you could have 2 times x, which is the multiplication part, or, and it says addition, but addition and subtraction really mean the same thing, right? Because you can add a negative, which really is subtraction, but that's pretty much it. It means that you're, multiplying or adding these things with real number coefficients. So those are the numbers out front, right? So they have to be real numbers. So it could be like a 2, but like in this case, it's even negative 3 over 2. So that's still a real number. Whole number exponents. So it's not allowed to have something like x to the power of 3 over 2 plus like 2x or something. That's not a polynomial because of the fractional exponent there. It has to be a, 1, 2, 3, yada, yada, yada. And 2 variables. So the 2 variables part just means like a y and an x, right? So that makes it a polynomial. And then the degree of the function is the biggest exponent. So I'll do more examples of that. But what you would say here is that this one would be a degree 1 because the biggest exponent on it is 1, right? That's the biggest one. The next one is 2, so that'd be a degree 2. And the next one is 3, so that'd be a degree 3 polynomial, making it a cubic function. All right. Now, looking at these graphs, notice, right? So this graph here is this graph. It's that top one, right? And this is like a little bit of review. This thing is going from the bottom up to the right. Well, that's because it has a... So if I had something like this, y is equal to mx plus b, right? The way we used to look at it. Remember the slope, how the slope was like what sort of angle it had going up and down? So this number here, right? This is like 1 out front of this one. So what that would mean is this thing goes over 1, up 1, over 1, up 1, right? So that's going to be the idea there. So it's going to start low and end up high. So yeah, I'll go into that a little bit more later, but yeah, so it goes like up a hill like that, right? Positive slope means you're going to be like going up a hill. Now the next one, you've got a negative, a value there, or what we used to call m. Well, that thing's going to go down, right? That thing's actually going to go down 3 over 2, down 3 over 2, right? So that's going to be going from high to low. All right, so that's the general way the graphs will look here. Now, when we get into the quadratic ones, if you remember this from last year, my little rule was if it's positive out front, if there was like a little positive sitting out front of this guy, like right there, then the graph is being positive. It's like a happy face, right? So that's the way it would open. So that's this one, right? It's going to open upward, right? Really big happy smile face. Okay. And the other one, right, for the other graph here would be negative. So he's being negative. He's being all frowny. So that's why this will be a frowny face one. Okay, so that's how you can remember those quadratic ones really easy. Now, cubic functions, the way I like to remember it, they're actually a lot like your linear ones, right, from this one. So this one, you know, if it was positive out front, it would go up. Well, that's generally the way these ones are going to work too, right? If it's positive out front, there is a little squiggle in the middle, but in the end, the thing really does just go like low and ends high, right? It's like the same type of thing with a little squiggle in the middle. And then same with this one. There's a negative out front. So then this thing is going to go generally downward, right? It's kind of like this one from the other one, how it was negative. But again, there's going to be a little squiggle involved. We don't need to know too much about the squiggle, like where the squiggle is going to be and all that kind of stuff. We just need to know almost that there just is going to be a squiggle in it. All right. Now, looking at these graphs, we've got this was a degree 1 polynomial for all of these ones because it had the biggest power was 1, right? And then the parabola is a degree 2 because they were all squareds for that one. This one's degree 3 because of the biggest power on those. Maximum number of x-intercepts. All right, so if you think about this logically, for this one with a line, how many times can a line cross the x-axis? Well, once, right? It can cross right there. So only one time. A parabola? Well, a parabola can go through it 1, 2 times. It could also miss it altogether, right? You'd have 0, or it could come down and just touch, and then you'd have 1. But the maximum number of x-intercepts would be 2 there, right, for both of them. And then with this one, you could have 3, right? Because if the x-intercept was like right in the middle there, then it could cross 1, 2, 3 times. Okay. Now the y-intercept. These ones are super easy to find the y-intercept of all these graphs because the y-intercept is always going to be your constant term on the end. So it's this last term on the end of all of them. So in this case, this would be, you know, a half, right? So this thing would have crossed at a half right there. This one would have been 6, so it would have crossed right at 6. Well, this top one maybe isn't so easy to see, but actually it would have crossed right at 0 because I could say plus 0 on the end, and that would have crossed right at 0 too. So it's always the constant term on the end. All right, let's get into a little bit. So characteristics of polynomial functions. So just to kind of go, we've actually done this before in previous years. Let's just do it again. So your number out front, well, any of your numbers out front, they're always called coefficients, right? The numbers that you're multiplying your variable by. But the one out front is actually called a leading coefficient as a special name. So it's your leading coefficient, okay, which would make that one just a coefficient. So sometimes you say the coefficient on the x term, right, is how you describe that one. The number on the end that doesn't have any variable attached to it, like no x, I mean, that's the constant term. And we've talked about this already, but the degree would be the biggest exponent. So that'd be the degree. Okay, maybe some other things here I'll just kind of talk about. I won't write down, but just remember that these are terms, they're called, right? Whenever it's separated by like an addition and subtraction, those are referred to as different terms. And then maybe the other one to kind of go over quickly here too, this thing could have been written out like different. It could have been like negative 24 plus 2x squared plus 2x, right? That's actually the same thing because remember, we can just like move these things around as like pieces. You could jumble those around. I'll put this one to the front, you know, this one in the middle, and you'd end up getting it looking exactly like this one. So even though it was written all jumbled like this one would still be a degree of 2, right? It's just kind of written a little bit in a different form there. All right, so now moving on to the graph. So just to remind you what different parts of the graphs are. So your x-intercepts, let's just like point them out on the graph here. So those would be your x-intercepts. So that'd be 1. So that'd be an x-intercept. And that would be an x-intercept. You would also have a y-intercept, which is on the y-axis, right? Like where it crosses. That's going to be your y-intercept. I made this probably a little bit too close, but if you can remember from last year, right where this thing starts to turn back up again, that's called the vertex. Right? That's it. And the vertex can either happen in a minimum like this, or it could happen in a maximum, right? And what's next? Axis of symmetry. So the axis of symmetry is actually the line that would cut this thing in half, straight up and down. Right? It's that line right there. And that axis of symmetry would happen, well, it would happen at the x value of the vertex. It would also happen right halfway between these two x-intercepts, right? That's what's going to cut this thing in half. So you guys might have to find those out here and there. Actually, I do one below, so I'll tell you more about that in a minute. But anyway, so your axis of symmetry would be an equation of a line, but just remember for this one, it's a straight up and down line. So this would be something like x is equal to -1, right? Instead of y is equal to -1. If we want a line going straight up and down, it'd be x is equal to, and that would be like that dotted line there. That's actually not right. Like it doesn't end up being -1, I don't think, but well, maybe it does. But yeah, that's the idea. So now domain and range. So we'll have to get used to this one a little bit. So the domain of any of these graphs is actually pretty simple, right? Especially if it's just one that's like in a calculator or something that doesn't have any like real world restrictions on it. The domain are all of the different values that x is allowed to be. So what is x not allowed to be? So domain is going to be like left and right. Okay, so in this case, you guys can probably see your domain is going on forever this way. That's what like the arrows in the top that I just drew mean. So if it goes forever either way, then like it can go as infinitely far to the left and I'm still going to have a value. It can also go infinitely far to the right and I'm still going to have a value. So in short, what we say is that x is a member of the real numbers. It just means anything. Okay. The range here now. So the range is going to be everything that y is allowed to be. So now that is always going to be what you have to figure out where the vertex is. And then in this case, it would be everywhere above it, right? So you can't have any y values because like the graph doesn't exist down here, right? But you do have y values up here. I'll do some more examples of that in a minute. But and then behavior of graph. So the behavior of the graph is going to be saying how does this thing look, right? Like it starts where and ends where, right? So in this case, you could say, let's just actually do this one for this graph. And maybe before I get going here, let's talk about the quadrants, because the quadrants on our graph are a little bit weird. I drew that kind of funny. This is quadrant 1. And I'm going to do make it like Roman numerals. So quadrant 1, quadrant 2, quadrant 3, and then quadrant 4. So it's kind of funny. It like starts here and then counts this way. It's like 1, 2, 3, 4, right? Okay, so now that we know that, or we remember that, then we can say this thing starts in quadrant 2. So like quadrant 2, and then ends in quadrant 1, right? And it's just really like this part, it can be written different ways. And even in your assessment, I think it says starts high, ends high, right? There's different ways to say it, but that's the idea, right? It's just kind of talking about like, how does this graph generally look? All right, factored form of a quadratic function. So now we're just looking at quadratic for a second. So we're looking at these exponents at this one, right? So this is a quadratic, so it's going to be a degree 2. Now we've done a bunch of factoring so far. So if you factor this, I won't actually factor it because I already have it factored below. But if you factor that, it would look like this, right? Now, when it's written out like this, let's sketch this quick. So if I sketch this thing would like there and there. I'll explain what I'm doing in a second here. And go, oh, that was terrible, but you get the idea. This thing is going to cross in two places, right? And you can imagine here that when the y value, right, when the y value is 0, then the x value would be at both intercepts, right? So what we can see is if I just write this out a little bit more, instead of an f of x, I'm going to say, okay, f of x or y, same thing. I'm going to say, okay, when that's 0, then 2, and then x plus 4, x minus 3. So maybe this looks a little familiar from what you guys were doing before. Actually, it should. I'm looking for, well, what numbers would x have to be in order to make this equal to 0, right? Because if I threw a 3 into that, right, that'd be 3 minus 3. That would make this whole thing 0, which would make the whole thing 0, right? So that would make this true. So one of my answers here would be x is equal to 3. And then from this one, x is equal to 4, right? And I made that a little bit more complicated than it needs to be in the end here, because you can just kind of see that my answers for what my x-axis or my x-intercepts will be is going to be like the opposite of the signs, right? So whatever the signs are, it'll be the opposite of that. Okay. Yeah, exactly. Yeah. So -4 and +3. Yeah. Okay. So you can write this two different ways. So in your guys' assessment, you'll see too that sometimes it'll ask it, it'll be like, okay, x is equal to something. So that's true, right? You solve for it that way. But another way is also just to write the points themselves, right? So because these are actually points, these x-intercepts, like this would be the point -4, 0, and this one would be the point 3, 0. Okay, so those are actual points that you could write down. All right, now the vertex of quadratic functions. So what we can do with this one is, I'm going to sketch this out a little better actually. Do it again here. God, I cannot draw a straight line. There we go. Okay, so let's write those again. So I know here that I've got, a -4. So maybe I'll draw that right there, like -4. And then this one at 3. And how do I know what opens up or down too, by the way? Well, again, that number out front, I'm looking at a smiley face, right? That's a positive. And I could distribute everything in, right? Distribute that 2 into there and then distribute that into this one. And I'd end up with like something like 2x squared and then plus something x, yada, yada. But either way, this thing's positive, right? So I know this thing's opening up. Okay. So now that I have my x-intercepts and I know it opens up, I know my vertex will end up being on this side of the line, right? Because it's going to be in between these two. So to do something like that, right? So right here, this was at the point, -4. And right here, this one was at the point 3. All right. And I'm looking for my vertex. I'm looking for this point down here. So it's going to be something, comma, something. And I'll write a V there for vertex. So there's an X value and there's a Y value. All right, let's see if we can figure this out. So this X value, you can imagine if I had my like axis of symmetry right down the middle there, you can see that dotted line I just drew, that's halfway between these 2 points. So if I want to figure out what the X value is right there, right between those, then I need to find, well, really the average between those 2 numbers. So how can I find the average between 2 numbers? So I want to find, well, here's what we do. We say both numbers added together. So -4 plus 3. So -4 plus 3. And then if you want to find the average between 2 numbers, you divide by 2, right? So in the end here, this is going to be -4 plus 3 divided by 2. So you end up with, well, -4 plus 3 is -1 over 2. So I end up with -1/2, right? Or it'd be the same thing to say x is equal to -0.5. Either one. Okay, so now what does that do us? Well, we found this, right? This number right here, right there, that was negative 0.5. And that makes sense. It's right between those numbers, even intuitively there, right? So if that is negative 0.5, then that is the same number all the way like over here, right, at our vertex. So we just found the x value of our vertex is negative 0.5. Zoom in there a bit. Nope. Negative 0.5. All right, so we found that one. Now I can find my whole vertex here if, well, here's what we'll do. If you know any value of x in an equation, all we got to do is just plug that in, right? There's our equation. Let's just plug in an x and figure out what we get out for y. So that'll do it. We'll be able to figure out what this y value is. Okay, so we'll say f of negative 0.5, right? That just means I'm putting in negative 0.5 into the function. And that's equal to 2. And then instead of an x, I'm going to put in negative 0.5, right? Put in my x value there. Plus 4. And then negative 0.5 minus 3. All right, what do we get there? So we'll go 2. Okay, so you put it all in. We end up getting f of negative 0.5 is equal to negative 24.5, right? So that's my y value, okay? So there, so we figured that out. So our vertex, I'll just write it out, the vertex again. So v would be negative 0.5, comma, negative 24.5. And that seems to make sense. It's going to be a negative and be down there, right? All right, so now that we have those numbers, now that we have our vertex, what you guys will have to do, like we'll be able to figure out our domain and range from those. Really our range, our domain's really easy. Our domain, I'll write like this, domain will just be, and yeah, just, you might want to just memorize this one. Quite often, x is a member of the real numbers, right? Range takes a little bit more thinking. So the range is going to be, okay, well, what's the range going to be? Well, let's look at this point. So we figured out that was negative 24.5. So what that means, if this thing opens up like it does, then this is the very bottom of this graph. It's never going to be any lower than that. So we're going to say y has to be greater than or equal to the y value at that point, right? Negative 24.5. And then you could write down where y is a member of the real numbers, right? I don't care too much about that part. Tack it on the end if you like. But it's really this part that's the important bit, okay? All right, so that's it. Now, factored form of cubic functions. So good news is you guys don't have to actually factor these. Like I'm not going to ask you to get something crazy like x to the 3 plus 4x squared minus 3x plus 2. I'm not going to get you to factor that, right? These are actually quite difficult to factor. But what you guys are responsible for knowing is what to do with it when you see it, right? So if it's already factored, do you know what's going on there? Like what's happening? The x-intercepts are actually pretty easy. It's the same as factored form from above. The x-intercepts are going to be the opposites of these pieces here, right? So in this case, what value would I have to put in for x to make the whole thing 0, right? If I made this side 0, well, that'd be negative 4, right? So it'd be x is equal to negative 4 from that one. You have x is equal to 3 from that one. And then x is equal to 2 from that one. So those are my x-intercepts. This thing would cross at all those places. Okay. Now, what is the y-intercept? Okay, this one, I can't actually see from this form anymore. It's actually quite easy to find the y-intercept if I had, let's say, like x cubed plus x squared plus 2x minus 4, something like that, right? When it's in standard form like that, it's always going to be the number on the end. But when it's in factored form, I can't actually see what the number on the end is going to be, right? So what we can do, though, if you if you can imagine, right? Let's say that this graph did something like, maybe, what does it do here? Something, or I wouldn't do that, but something like that. I don't know. It's not, but it wouldn't go through the middle. But either way, okay, either way, you can see that when this thing crosses the y-axis, right? When it crosses the y-axis there, that's going to happen when x is 0. Okay, so then what that means is we can just throw some zeros in for that. So let's write the function out. So I'll say f of x, or I'll just say y, is equal to negative. And then, like I said, I'm going to, instead of an x, I'm going to throw a 0 in. So that'll be 0 plus 4, and then times 0 minus 3, and then 0 minus 2. Okay, and then writing it out again, we get y is equal to negative, and then that's really just 4, right? 0 plus 4 is 4, and then times negative 3, and then times negative 2. So just careful with your negatives here. So we're going to have, I'll just tack this negative on the front for a second. 4 times negative 3 times negative 2 is going to be positive 24, and then that negative was still tacked on the front. So that this thing is going to cross at negative 24, or the point 0 comma negative 24. So my picture was terribly wrong, right? It would cross down here somewhere. Okay, now these guys, domain and range, they're actually even easier, because if you look at our graph of our new types of functions that we're dealing with here, right? These things go forever. They go forever both ways, right? They go forever in the x and they go forever in the y. So domain and range. So the domain, I can just say x is a member of the real numbers. I can actually say the same thing for the range now too. It doesn't have a bottom. It doesn't have a vertex, right? So that can be y is just a member of the real numbers, and just leave it at that. All right, now looking at this one, what are the x-intercepts now? So notice, I just want you to notice with the squared there, that we could have written this thing to be the same thing to say this. F of x is equal to 2 times x plus 2, x minus 3, and then again times x minus 3, right? Just writing that twice, because that's what it means to square something, right? So that'd be the same thing. So if I did the same as before, I can see from this one, I've got x would have to be equal to negative 2. From this one, I'd have x has to be equal to 3, and then this is the same thing, right? X is equal to 3. So it's like we've got two occasions of the same x-intercept there. So technically what happens there, we won't get too much into it, but what happens is that this thing only crosses twice. So you'd have one where it crosses there. You'd have one where it crosses, well, it doesn't cross, but one where it's there. This thing would do this. It would go up. Oh, it would go up. It would come down, and it actually just touches right there and then goes back up again. And that's what, it doesn't actually cross. So there is only two. There's this one where it goes through, and then there's this one where it just touches and then deflects back the other way. So that's really what's happening there. But either way, there only ends up being 2 x-intercepts at that point. All right, there's negative 2 and there's 3, and that's it. All right, what's the y-intercept? So we'll do the same thing as before. We'll say y is equal to 2, and then instead of an x, I'm going to put a 0 in. So 0 plus 2, and then 0 minus 3 squared. So cleaning this up, we got 2 times 0 plus 2 is just 2, and then negative 3 squared. Okay, so that would just be, well, we'll do it again. 2 times 2 times negative 3 squared is 9. So that's going to be 2 times 9 is 18 times 2 is 36. So we get y is equal to 36. So that would be at the point 0, comma 36. All right, and then domain and range, probably don't need to do this again. Same as above, right? Anything. It goes on either way. It goes infinitely far down, and it goes infinitely far up and left and right. So it's going to be any of the, like x is a member of the real numbers and y is equal to a member of the real numbers. All right, so An equation of a particular cubic function is this, right? So you got this going on where m and p are different whole numbers. This is an old diploma question, by the way. And it says, which of the following could be the graph of this polynomial? So how can we tell here? They haven't really given us numbers, but these are numbers, they say, right? They're all just different whole numbers. And so I know this thing is going to be cubic. And how do I know it's going to be cubic? That's because there's 1, 2, 3 terms there, right? So if you expanded this thing all out, right, then you're going to end up with something at the beginning of x to the power of 3, and then like a bunch of stuff, like other stuff going on too, right? But in the end, it's a cubic function. So I know it's going to be one of these squiggly guys. They didn't really, like, they're all squiggly, so that doesn't really narrow it down for me. But I also know that this thing, well, x minus m. So let's actually just put in like numbers for a second. Like what if I had, so m and n, no, they wouldn't necessarily be the same. Actually, they're not the same. But here's what we can do. We can say, what if we had x minus, I'm going to put in two different numbers. What if we had like x minus 3, and this was like x minus 2, and this was like x plus 4 or something, right? So now we can see from this thing that, okay, this one, x would have to be equal to 3. This one would be x would have to be equal to 2. And this one would be x would have to be equal to negative 4. And I know I just threw random numbers in there, but what we can take from this is that these two are going to end up positive, right? Those ones, no matter what numbers I threw in there, right? That could have been 6 and 9 or any number. These ones are going to be positive, and this one's going to be negative. So looking down here, I know that I'm going to only have one negative value for x, and I'm going to have two positive values for x, right? So it's really down between this one. It's down between C and D at this point, right? Because this one had two negative values, right? Two negative values, but I'm only going to end up having one negative value for my x at the end there, right? So it's down between C and D. And then the next little hint here is, which way does this thing open? And it's positive, right? Out front, there's no negative out front. These are all going to be like, when I multiply all my x terms together, that's going to give me a positive x cubed term, right? So what I was saying above is the way that these things work is it's kind of like the linear ones, where it's going to start low and end high. This thing will generally go up and down like this. If it would have been negative out front, it would have went like, or would have went down the slope like this with a squiggle in between. Okay, so that's the idea. So it's got to be C then, is the only one that it could be. Okay, last one. So the following statements were made about the polynomial function yada. So it says the x-intercepts are -3 and 5. The function has a degree of 3. The domain is that, and the range is that. And it says the statements that are true are. So let's go through piece by piece. So the x-intercepts are -3 and 5. So let's just double check this, right? It's really the opposites of these things, right? So this would be x has to be equal to 5, and x has to be equal to -3. So that looks good, right? This one would just have like, that'd be one of those touch points again, where it just touched and went back up. But in the end, yeah, there's only 2. So that's true. It says the function has a degree of 3. Now this one might throw you off because I'm looking at this and there's only like an exponent of 2, right? But this one has an exponent of 2. Like you could write it out like this, like x minus 5, x minus 5, x plus 3. That'd be the same thing, right? Just writing that squared term back out again. And you can see it a bit clearer here now, right? That you'd have x times x times x after you expanded all of this. This would be x to the power of 3 once you expanded it. So this thing does have a degree of 3. Okay, the domain is between -3 and 5. I don't know about that one, because these things don't really work that way, right? This thing would be doing something like, doing something like this. This would actually be just x as a member of the real numbers, right? This would be anything. Okay. Now, the range is any real number for this one. So, yeah. So 1, 2, and 4, so it's got to be C. Yeah, so the range, by the way, yeah, up and down. So everything is up and down. So hopefully that one made sense.